Hey Siri, call Selma. Good morning. Did you see anybody by chance come to my classroom? Oh, I, I got somebody just added in, so I'm hoping they're coming shortly. All right, thanks.
Your seatbelt on, Sophia?
I wonder when she's gonna realize that.
Morning, Jennifer. Morning, Amanda.
Good morning.
Hoping the high school kids will be joining us shortly.
Okay.
So we have 9 in the class this time. So how was your vacation?
It was good. It was long.
Ready to get back to class?
Oh yeah, before I forget anything.
Right. Well, I pulled up the syllabus just to kind of show you an idea. This is in Canvas about what our plans are for this semester. So did you get the full year homework last semester?
I did.
Okay.
Yeah.
So hopefully it should continue on and you should be able to access Achieve without any issues. But if you have issues, let me know. I've already got chapter 11, should be available to you. Not sure where my high school kids are. Do you have snow there in the Globe? Or bad weather?
There's a lot of rain in San Carlos. I think we're put on the flood warning right now.
Okay.
They were getting ready to start evacuating if it doesn't stop raining. No one's allowed in or out right now.
Okay. Maybe that's why they're not joining us. All right, we'll go ahead and get started, and hopefully they'll be with us shortly. So I just wanted to go over the syllabus real quick. So this is in Canvas. As far as the first part, it's essentially the same, except we're now in Chem 152 instead of 151. So just continuing on. Grading scale is the same textbook, same homework through Achieve. And if you paid the $64 for the entire year, you should be able to just continue on into the 152. You'll just have to add the different section. And if you didn't, then you'll have to pay for it again. As far as exams, some of these may be take-home paper instead of Achieve. So that will be a little bit different. And then our schedule, had Martin Luther King holiday yesterday. We're starting with chapter 11. We're going to have our first lab on Thursday, so that will be in the lab room. So if you see a blank spot, that just means we're going to continue on with chapter 11. Monday, I have to attend where my wife's cousin passed away this weekend from cancer, so we're going to attend her funeral on Monday, but it starts at 10, so I'm going to have to Zoom, so I wouldn't have time to get back from Globe to the funeral. So we're going to Zoom on Monday and Tuesday. Then actually on Thursday, I have to be in Payson at 9 o'clock. So we're going to Zoom on Thursday as well. So next week we'll have 3 Zoom days, and then Wednesday we'll have a lab. Then Monday's normal, and then the 31st Zoom. And then we're going to try for our field trip on February 2nd to the mine. So we tried that last semester. I think we've got it set up so we have transportation now. Then when we get spring break is March 13th. When we get to March 27th, I have a meeting in Chicago with the Higher Learning Commission, which is our creditors. And so I'm going to have a substitute, so we'll be in person, but there'll be a substitute in class those 2 days. And then the same thing, April 3rd, 4th, and 5th, I have to visit another community college to evaluate their school. So we'll have a substitute those 3 days. So end of March, 1st of April, we'll still have class, but there'll be a sub because I won't be in town. The rest of the semester should be fine. We are going to go to Engineering Day in Thatcher on March 2nd. And then there's the Student Chemistry Adventure on April 27th, also in Thatcher. So we have 3 field trips. Then our final exam is scheduled for Tuesday and Wednesday. And then Thursday, we'll just have a celebration day that we made it through. And then graduation is on the 9th. So are either of you graduating this semester?
No.
No, not me.
All right. Well, you're making good progress. All right. Chapter 11. See if I can find it here. All right, chapter 11 is solutions. So tell me why you think a raw egg swells or shrinks when it's put in different solutions. Have
It's
you ever
porous.
seen that demonstration where you peel the egg off? I think Dr. Terfin may have done this before, where he peels the raw egg, and then so it just has the membrane, and then puts it in a solution. Any of you seen that before?
Yeah, he did. I think one was in vinegar, the other one was in like Karo syrup.
Correct. That was the experiment. So
Yeah.
do you remember why it shrunk in one and why it got larger in the other one?
I can't remember specifically, but my guess would be because it's a porous object.
Right? So it has a membrane, so the water can flow both in and out of the egg. So if it's more concentrated, if the solution of electrolytes is more concentrated inside the egg, then the water will flow into the egg to equilibrate it. So if they're the same concentration, so that'll make the egg get larger. If your concentration of electrolytes is larger on the outside, then the water is going to flow out of the egg to kind of neutralize or equilibrate the two solutions, and so it'll shrink. So it has all to do with solutions, solutes, solvents, and trying to reach an equilibrium. So a few definitions. Homogeneous. Amanda, what does homogeneous mean?
Then it's all the same size. Everything's the same.
Right, very good. So it's uniform throughout, so it all looks the same. So if I was to take a spoon and take a sample anywhere in that solution, it would be identical all the way through. So we have the solvent and the solute. So what's the difference between solvent and solute? This is like a review from last semester a little bit. So in this picture, if this is some sodium dichromate, the yellow stuff, and we're putting it in water, which is the solute and which is the solvent?
Is the water the solute?
Right. Good thought. The one that is actually doing the dissolving is the solvent. The one that's being dissolved is the solute. Or another way to think of it is the one that's in the smaller quantity is the solute. It gets dissolved into the solvent. So for example, we take Kool-Aid, we want to make some Kool-Aid, we take sugar, we dissolve it in the water. The water would be considered the solvent. The sugar is considered the solute. All right, what about saturated and unsaturated? What's the difference between those two words?
Saturated means that it's been absorbed, and unsaturated means it hasn't.
All right, so if you go outside in the rain, you might say, I just got saturated. Just means I
Indeed.
got covered with rain. So saturated means you have absorbed or dissolved the maximum amount of solute possible. Unsaturated means you have not dissolved the maximum amount possible. So example, we're making our Kool-Aid again. And let's say we take some sugar and we pour it in the water and we stir it up, it all dissolves. Is that unsaturated or saturated?
Saturated.
Saturated.
Okay. What if I add more sugar and it still dissolves?
Still saturated?
So it has not become saturated until a point where you add a crystal of sugar and it floats to the bottom and it no longer dissolves. That means it's now holding the maximum amount of solute possible. So that is saturated. Unsaturated means you can still add more and it's still going to dissolve that sugar. So until it reaches the point where some of the solid goes to the bottom and settles, it is unsaturated. So your Kool-Aid is an unsaturated solution, but at some point, if you keep adding more and more sugar, it's going to get to the point where it is saturated. So one way to tell whether it's saturated or not is add some more solute. If it dissolves, it was unsaturated. If it sinks to the bottom, it was saturated. And if you add a crystal to it and a whole bunch more precipitates out, that means it was supersaturated. And honey is an example of supersaturated because it looks like it's a liquid, but if you let it sit over time, it'll start crystallizing, which means it was supersaturated. So saturated contains the maximum amount of solute. Supersaturated contains more than the amount possible. So that means when you add a crystal, it all starts crystallizing again. And try and this movie's not working, so I'll try and show you that in class tomorrow. Good morning, Grace.
What did you do? No.
All right, energetics of the solution process. The higher energy is the red
Them.
part, lower energy is blue. So as the molecules you add energy to it, then you're going to kind of break some of those intermolecular.
Go away. What was no?
So enthalpy, once again, means the heat of the solution. So if the enthalpy is more negative, then is that exothermic or endothermic? When enthalpy is negative. Do you remember?
Exothermic.
Right, so if enthalpy is negative, that means we are exothermic. So we're going to look at the energy of dissolving and kind of compare that as well throughout this chapter. But you're right, it is exothermic. So Grace, do you have the rest of the class with you or are you alone? So here's our supersaturated sodium acetate solution. This is a heat pack. So if you break the little seal in between, then the supersaturated solution will become saturated and it will release heat. So it's like a heat pack. So that's what I'm going to show you in class tomorrow. And it has an endothermic heat of solution because as it breaks, as the two solutions combine, then it absorbs that energy. So here we have our sodium acetate. We apply heat, our little clicker, then it breaks into its two ions. So because heat is on the left side, it's considered an endothermic or it absorbs heat. So if it's endothermic going to the right, that means it's exothermic going to the left. So if we take the two ions, combine them, then it's going to form a solid and it will release heat. So to make this work, we take our sodium acetate solution and we put it in some boiling water. And then the solid dissolves and forms the ions. So it's now a liquid solution. But then when I click it, then it goes the other direction and it forms a solid, which means it releases heat. So this is actually a reusable heat pack. So to reuse it, we just heat it back up, make it super saturated again, let it cool down. And then if we initiate it with the clicker, then it will release heat. All right, some of the colligative properties we're going to study in this chapter are vapor pressure. So if we add a solute to a solvent, so we add sugar to a water or we add carbon dioxide to water, then the vapor pressure is going to decrease. So if I add carbon dioxide to some water solution, then the vapor pressure of that gas is going to decrease because the gases are dissolving into the water. So think of it as you have a container of gas. So because the gases expand, you have high pressure. But if some of that gas goes into the water, then now you have less gas above the water solution, so you have less pressure. But what happens when you heat up a container or a soda and then you open the lid? Have you done that before? Or shake it up?
You increase the pressure.
Right, because the gas molecules are coming out of solution. Now you have higher pressure. So when they dissolve, you have lower vapor pressure. When they come out of solution, you have higher pressure. So you heat it up, that causes it to be less soluble in water. So it comes out and then it explodes when you open the lid. All right, melting point. So what is the melting point of water?
Zero degrees Celsius.
Correct. What if it's snowing outside? How do I get the snow or ice to melt? What do they do on the roads? Probably having to do this in Flagstaff and Payson right now.
Add salt.
All right, so if we add salt, so that's adding a solute to the solvent. So adding salt to the ice. If ice melts at 0 degrees Celsius and it decreases the melting point, maybe now it melts at -5 degrees Celsius or maybe -10 degrees Celsius. So that means instead of melting at 0 degrees Celsius, it will actually start melting when it's colder at -10, which will cause the ice on the roads to start melting sooner. So adding salt or cinders like they do in Flagstaff, adding some kind of solute to the ice causes the melting point to get lower, which allows it to start melting. So it melts at a colder temperature. Also, what's one way to make your water boil at a temperature higher than 98 degrees Celsius? Have any of you ever added salt to your spaghetti or salt to water to try and get to boil at a hotter temperature? You could try that at home. Yeah, Jennifer?
Yeah, I've added salt to my pasta, but never thought about it.
Yeah, by adding salt to your water and then adding the spaghetti, it's going to actually boil at a hotter temperature so it'll cook quicker. So if you want your water to boil at a hotter temperature, then just add some salt to it. So it does two things. It lowers the melting point and it raises the boiling point. And the reason it does that is because the solute disrupts those intermolecular forces with the water so that they can't bond as easy, so they can't crystallize or they can't break apart to boil. And then osmosis or osmotic pressure, it makes this possible, and that's when the water is able to flow across a membrane. So all of these are called colligative properties. And these colligative properties depend on how much solute and relative to how much solvent you have. So it really doesn't matter what kind of solute you have, it just matters how much solute you have. So questions so far? Looks like we lost Grace. All right, concentration units. This is a review of last semester also. So the one that we used last semester was molarity, but molarity is not always the best concentration unit to use when we're talking about how much solute per solvent. So we have a new concentration, and that is mole fraction. So if we have a mixture of 3 solutes, A, B, and C. So to find out how much A is, you take A divided by the total. If you want to find the mole fraction of B, you take B divided by the total. And the same with C, take C divided by the total. So if I wanted to find out the mole fraction of males in the chemistry classroom, I would take the number of males divided by the total number. If I want females, I would take the number of females divided by the total number. So that's what mole fraction is. And then molality, which comes from mole fraction, is the moles of solute divided by the kilograms of solvent. If you remember molarity, it was moles of solute divided by liters of solution. In this case, it's moles of solute divided by the mass of the solvent. So and a lot of times it's very similar because our solvent is usually water. And we know that 1 gram of water is 1 milliliter. So sometimes molality and molarity are very close to the same. And then weight percent is the grams of solute divided by the grams of solution multiplied by 100 to make it 8%. And we did a little bit of that last semester. All right, so here's our first problem. We're going to dissolve 62.1 grams of ethylene glycol, which is 1 mole, in 250 grams of water. We want to calculate the mole fraction, the molality, and the weight percent. So we have 62.1 grams of ethylene glycol, which is 1 mole. And we're going to do that in 250 grams of water. We want the mole fraction and the molality and the weight percent. We'll go back one, so you have the formulas again. All right, so mole fraction. Tell me what to do. There's only two of you, so you have to answer all the questions between the two of you. Can't hide today.
Is mole fraction is at 62.1 divided by 250?
All right, that's close. So you're actually looking at, so let me go back to mole fraction. So mole fraction is the moles of A divided by the total number of moles. So we need to put everything into moles. So do I know, so it'd be the moles of solute divided by the total number of moles.
So total number of moles would be 2.
Right. So for ethylene glycol, the solute, how many moles do I have?
1.
So it's going to be 1 mole divided by the total number of moles. Now, how do I know how many moles of water I have? We've got to change grams into moles. So do you remember how to change grams into moles?
Gotta take the mole bus.
All right. So see if I got my periodic table. Remember how much hydrogen weighs?
1.
And we have 2 of those. And how much does oxygen weigh?
16.
And we have 1 of those. So 16 plus 2, we've got 18. So 1 mole over 18 grams. So I'll cancel the grams. So 250 divided by 18. Either of you have your calculator?
Yes.
It's 13.88.
13.88.
Yep.
So if I want mole fraction, it's going to be the moles of the solute divided by the total moles, which is 13.88 from the water and 1 from the solute. So it would be 1 mole over 14.88. So you notice we did the moles of solute divided by the totals. We have to add the solute and the solvent together. And it's going to be a decimal number. What'd you come up with?
0.067.
Right, and because it's mole fraction, moles cancel, so there are no units, just 0.067. Right, molality. Molality is equal to moles of solute divided by kilograms of solvent. So once again, our moles of solute is 1. Now, how many kilograms of solvent or water, how many kilograms of water do I have? So we're in
Point.
grams, 250 grams. I need to change that into kilograms.
Is it 0.250?
Correct. Good job. So move your decimal 3 places, change it from grams to kilograms. So 1 mole divided by 0.25 kilograms.
It's 4.
It's 4 small m, or 4 moles per kilogram. So small m is molality and capital M is molarity. So 4 moles per kilogram. And then the weight percent. So weight percent is mass of solute divided by the total mass. So what was the mass of my solute?
Was it the 13.88?
13.88 is moles of water. So I want the weight of the solute.
Oh, 250 grams?
250 grams is the mass of the solvent.
62.1.
Right, so water is the solvent, ethylene glycol is the solute. So the solute, 62, you say 62.1 grams divided by the total mass. So the total mass is the mass of the solute plus the mass of the solvent.
So the total mass is 312.1. And the weight percent is 0.19.
And then we want to change that to a percentage.
19%.
So that means we are 19% of the solution is ethylene glycol, which means 80% of it is water. So can you think of any situations where you would mix ethylene glycol and water together? Do you know what ethylene glycol is? Either of you?
Not off the top of my head.
No, I don't.
All right. Do you drive a car?
Yes.
All right,
Oh, is it gas?
how do you keep the engine from overheating?
Oh, antifreeze?
Yes. So ethylene glycol is antifreeze. So when you buy it at the store, you can either buy straight antifreeze, and then you have to mix it with water, or you can buy it already pre-mixed. Either of you pay attention to what the percent is of the mixture when they pre-mix it?
Uh-uh.
All right, so next time you buy antifreeze, look at it, but it's going to be 50% ethylene glycol, which means this one right here is 19%. So 50% would be 50 grams of ethylene glycol and 50 grams of water. So equal amounts of both of them. So a 50-50 mixture, if you were making your own mixture, you would take the ethylene glycol and then add the same amount of water, and now you've got a mixture. And you pour it in your radiator. And why do I add the ethylene glycol to the water? in my radiator? Why don't I just add water? What'd you say the name of this stuff was again?
Antifreeze.
So what do you think it does?
Keeps it from freezing.
Right. So anti-freeze. So stops it from freezing. So remember, we said if we add a solute to a solvent, it lowers the freezing point. So now instead of the water freezing at 0 degrees Celsius, if it gets really cold outside and it freezes, the water in the radiator is not going to freeze because we have anti-freeze in there. We've added solute to it, which has lowered the freezing point, so it doesn't freeze in your radiator and crack your radiator. Also, not only does it lower the freezing point, what does it do to the boiling point?
Raises it.
Right, so we lowered the freezing point and it raises the boiling point. So now instead of water boiling at 100 degrees Celsius, now if my radiator gets hot, it's not going to boil because I've got the antifreeze in there, which is raising the boiling point. So now it's going to boil at maybe 120, 130 degrees instead of 100 degrees. So they discovered that the ethylene glycol does a good job of lowering the freezing point. So when you're in cold weather, it doesn't crack your radiator by freezing. And it raises the boiling point. So when it's hot outside, it doesn't boil off all of your water. And you may have seen, or your grandparents may have known times where they've had to add water into their radiator. And that's when it starts boiling, when you have problems. All right, questions on our mole fraction, molality, and weight percent.
No.
No.
All right. I think this just goes through how they did it. So you came up with 13.88 when you changed it to moles. You got 0.067. So adding the mole divided by the total moles. And you got 4 molal solution. So it looks great. Then you had 19.9%. So you told me 19, so we were off a little bit. So probably just a rounding error on that one. All right, dissolving gases and Henry's law. So tell me what happens to a soda when you put it in the refrigerator compared to what happens when you leave it outside in the sun. And then you open it.
If you put it in the fridge, it should lower the pressure inside.
All right, lowers the pressure, which means the gases, the carbon dioxide has dissolved into the water. If you heat it up,
That'll increase the pressure.
right, so if you heat it up, the gases come out of solution, which creates more pressure. Then you open it, sprays everywhere. I wish my videos were working, but. So the gas solubility of a solution is equal to some constant, which is Henry's constant, times the pressure of the gas. So this is Henry's law. Solubility is Henry's law constant times the pressure of the gas. So for oxygen, it's 1.66 times 10 to the negative 6 molar per millimeters of mercury. I'll record that. So the Henry's constant for oxygen is 1.66 times 10 to the negative 6 molarity per millimeters of mercury. So if the pressure goes down, then the solubility goes down. So if you look at this equation, gas solubility and pressure are those direct or inverse relationships? Amanda, solubility and pressure, direct or inverse?
Direct.
All right, so if the pressure, say constant is 1, if the pressure is 5, what is the solubility?
5.
Right. Now, say K stays 1 because it's a constant. If you increase the pressure to 10, what's the solubility?
10.
All right, so direct relationship, pressure goes up, solubility goes up. Pressure goes down, solubility goes down. So here's Lake Neos in Cameroon. You ever heard of this lake?
No.
So this is a lake that had a buildup of carbon dioxide, and all of a sudden there was this big, huge carbon dioxide bubble burst. And so it released a tremendous amount of carbon dioxide and killed everybody in this area. Because carbon dioxide is less dense than oxygen, when it came out of the lake, the carbon dioxide settled around the lake, and so anybody in this area was killed.
Whoa.
So you can Google Lake Neos, Cameroon, and see what happened. It's because of all of the carbon dioxide that built up. So what they do now is they actually have little vents that allow the carbon dioxide to release at a constant rate, so you don't get a buildup of carbon dioxide. All right, so here's an example of little water molecules. So in the bottom part, we're saying they're in solution or in liquid state. On the top, they're in a gas state. So the water molecules can leave, become a gas. They can go back in the water, become a solution or liquid. So this is the liquid vapor equilibrium. So think of your shower. When you take a shower and close all the doors, what happens to your mirrors?
I think it's steamy.
Right. And then if you let it cool down, what do you notice starting to happen on the mirror?
Condensation.
Right, so you get condensation. So there was all of this water that was a gas in the room, and then because the window or the mirrors are cold, when the gases hit that cold surface, then they condense on the cold surface, turn to a liquid. So that's kind of the equilibrium between it being a gas and being a liquid. So here's another example where here we have a liquid, and you notice we've got the ones in the top part are the gas. So we have a lot more in the liquid, a few in the gas state. And then we add some solute in there, some little red particles. So these are the solute molecules. I wish that was working again. So the vapor pressure depends on the number of water molecules per solute molecule, or our little equation. The pressure of the solvent is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. And this is Raoult's law. I'm going to write that one down, Raoult's law. So the pressure of the solvent is equal to the mole fraction of the solvent times the pressure of the pure solvent. So as the mole fraction of the solvent gets higher, the vapor pressure is going to get higher also, because those are also direct relationships to each other. And because the x is always going to be less than 1, any number less than 1 times the number is going to make the left side smaller than the right side. So your pressure is always going to be smaller than your pure solvent vapor pressure when I add some kind of a solute to it. So whenever you have a solvent over a solution, your pressure is always going to be lower. Right, so here's our problem. Remember, we had 62.1 grams of glycol and 250 grams of water. What is the vapor pressure of water over the solution at 30 degrees Celsius? And it says the vapor pressure of pure water is 31.8 millimeters of mercury. So to do that, we go back to our mole fraction. So mole fraction is when we had moles of solute over the total moles of water. Moles of the solute was 1, total moles was 14.88. So we got 0.067. That was our mole fraction. So we took the 0.067 and we know that the mole fraction total has to be 1. So if I know the glycol or the is the 0.0672, then I can figure out the mole fraction of the water. So if glycol is 0.0672, so we found the mole fraction of the solute was the mole fraction of the glycol, 0.0672. What is the mole fraction of the water? If glycol is 0.067, what is water? The solute plus solvent has to equal 1. So solute was 0.067. What is the solvent going to be?
0.9328.
All right, so adding those together should equal 1. And remember, Raoult's law was pressure of the solvent is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. So in this case, we found the solute 0.067, so I had to subtract from 1 to find the solvent. So the solvent is 0.9328. And then the pressure, vapor pressure of the pure water. Go back to that one. It said it was 31.8 millimeters of mercury. So times 31.8, so 88 millimeters of mercury. Let's see, they've got 0.9382. Did I write that down wrong?
Yeah. I think.
Do I trust them? So we had 1 minus 0.067,
Yeah.
0.933. So, okay, they did it wrong. Do you notice that? In this slide? So 0.9328 is what we've got times, but then when they multiplied it here, they switched the two numbers, the 28 and the 82. So don't ever trust your book publisher. It's Harcourt Bracing Company, got that one wrong. So let's see if they, so if we got 0.9328 times 31.8, got 29.66. So it looks like they calculated it right. They just put the numbers down wrong. So 29.7 millimeters of mercury. So you notice the pressure when you added that solute is lower than what it started with, which was 31.8. So your answer always is going to be less. Looks like it dropped by about 2 millimeters of mercury. All right, and that's Raoult's law. So there's your introduction to colligative properties. So mole fraction, molality, weight percent, and Henry's law and Raoult's law. Then we'll do some more examples of those tomorrow in class. So we'll be meeting in our normal classroom in Globe tomorrow. Can both of you
Okay.
be there in class?
Yes.
All right.
Will tomorrow's class be available via Zoom?
It might be because I've got Anne Mary from Miami.
Okay.
It's better if we can, since there's very few of you, there's only 9 of you. The more we can have in class, the better,
Okay.
if it's possible.
Okay.
All right, we'll see you tomorrow.
Okay.
Tomorrow. Thank
Bye.
you.